Hi, Dr. Ogan.
Hi,
Hi. Yes,
nice to see you.
our speakers already here, so we shall start our webinar. Good afternoon, everyone. I would like to welcome you all to this webinar, The Future of Medicine Updates on Protein Electrodynamics and Terahertz Medicine. I'm Dr. Wong from Association of Clinical Registries. We were established in 2005 via joint efforts of health and IT professionals with an interest in clinical databases and disease registries in Malaysia. Our society is motivated by increasing awareness of huge potential of data to serve as both powerful tools in both research and also servicing field. Please scan the QR code if you are interested to find out more about SCRM. Before the presentation begins, we have a few housekeeping notes to make. This webinar will be around 1.5 hours long, including a key topics and a Q&A sessions. Please do type your question in the chat box and we will do our best to address it during the Q&A sessions. This webinar will be recorded and the link will be shared. Now, please allow us to introduce our speaker, Dr. Ogan Gurel, our medical expert. He is the visiting professor at the Bridge International School of Business and invited teaching professor at DIGIST. He is active in innovation world, holding different posts such as advisor for Crest Malaysia for Digital Health Cluster. In the past 35 years, his experience spans across multiple sectors, including clinical medicines and also in the field of molecular biophysics. And he has worked with the Nobel Prize winner, Prof. Martin Kaplus, in biochemical science. Without further ado, I would like to welcome Dr. Ogan Gurel to deliver the presentations. Please, Dr. Ogan.
Thank you very much, Dr. Wong. It's a pleasure to be here with my friends from Crest and the others in Malaysia, and I believe we likely have audience beyond Malaysia as well. And thank you for the kind introduction and the opportunity to talk about this topic, which has been near and dear to me for many years, ever since my undergraduate years, actually with Professor Karplus, who was an inspiration, among others, for this ideas. And I'll share how that came about. So I want to thank you. I want to thank Crest and the other organizers for making this possible. And if I may share the screen.
Yes.
Is it coming up okay, Dr. Wong?
Yes, very clear.
Great. And Dr. Wong, did you want questions during the presentation, after the presentation? How would you like to, what do you prefer?
We will keep the question at the Q&A session. So Dr. Ogan, you can just proceed with the presentation.
Okay, thank you very much. So the topic for today is the future of medicine, update on protein electrodynamics in terahertz medicine. And it's an interesting topic because I had the great privilege of being a advisor for the digital health cluster with Crest. And you were mentioning also with the QR code and all that data and digital healthcare and so forth. And these areas that are of great interest to Crest and of course to many around the world, digital healthcare, are indeed part of the future of medicine. But today's topic is not so much about these digital technologies or artificial intelligence or wearables or IoT, things that are increasingly important and many people are already actually aware. This is about a whole new area of science and the way we actually do medicine. So that's why I call this the future of medicine. And some of it is happening now and some of it will be more futuristic. Now, the second reason why I think Crest is very important in as one of the stakeholders, if you will, or people that potentially are interested in this idea, is that this concept of protein electrodynamics that I'll be talking about and terahertz medicine is related to electronics. And obviously Crest has done an incredible job with Malaysia and the ecosystem, the electronics industry in Malaysia. And so there is some intersection with electronics. So I think in addition to healthcare, in addition to futuristic vision and in some of the aspects of electrical engineering and electronics, this is a very good fit. If you can see on this introductory slide, you see CREST, Collaborative Research in Engineering, Science, and Technology. You can see the positive and the negative, and it's made to look a little bit like an electric circuit. So it's a great pleasure, a great privilege to be involved. That's a little bit of background. Now I'll shift gears to a little bit philosophical. This is a quote from Immanuel Kant. Two things fill the mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. And he wrote this in his Critique of Practical Reason in 1788. And so you might wonder, when we talk about electronics and medicine, what does this quote have to do with this? And we'll get to that later on. So I just wanted to pique your interest a little bit with this very inspirational idea. Two things fill the mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. So by way of outline, there'll be four major parts to this presentation. I'll start with key questions, motivating questions, some of the fundamental science and ideas behind this, some actual research, both previous and ongoing, and then some applications, some of which may be interesting to the audience and other stakeholders to pursue further. So let's start with some key questions. Four questions. What is the future of diagnosis? Obviously, diagnosis is a very important part of medicine. And likewise, what is the future of therapy? What is the future of technology more broadly? And how does life work? These are obviously very big questions. This seminar is not going to answer them specifically all in its entirety, but these are motivating questions. And I think some of what we'll be talking about will have some impact on these questions. So first is, what is the future of diagnosis? And by diagnosis, I apologize, I mean more imaging. And on this chart, you can see the four modalities of X-ray, ultrasound, CT, MRI, and PET, and a timeline below. And if you look carefully, you'll see lots of technologies and lots of innovation, but there are essentially no new modalities, no new kinds of imaging since around the mid-1980s. An invention to some extent has stopped, as current innovation, you can see on the right-hand side, is largely incremental. So then what is the future of therapy? And by therapy, we mean drug therapies. And this chart, also a timeline, shows the number of drugs released or approved as a function of research dollars. And as you can see, the graph is decreasing, which means less drugs, more research dollars, more money. And ever since the turn of this past century, 2000, it costs about $1 billion to bring one drug into the market. And likewise, we can say to some extent, the diminishing returns that apart from incremental advances, innovation has largely stalled in biopharma. This is George Yancopoulos, the Chief Scientific Officer of Regeneron Pharmaceuticals. It's a very prominent pharmaceutical company that has that monoclonal antibody for COVID. And he writes, successfully inventing and developing any new drug or vaccine is probably among the hardest things for human beings to do. This is reflected in the numbers as by this chart. So when you see a chart constantly decreasing like this for half a century, one thinks, could there be another way, another method to do therapy? So the third question is, what is the future of technology? And as you saw in my background, I spent 4.5 years in the CTO office at Samsung, and I've been involved in the innovation world more generally, academically, practically, and business-wise. And we have techniques actually to predict the future of technology. Which sounds a little bit crystal ball-like, but actually there are methods, if you will, to see how technology will evolve. And one method is called TRIZ that works on the natural evolution of technology. For example, weapons get faster, more powerful, more distant, and technology just progresses in predictable patterns. So you have an immobile system eventually having greater degrees of mobility to ultimately an energy-based system. So we could apply this to steering wheels, to doors, and even to medicine. So if we look at medicine now, we have what we would call for the past 2,000-3,000 years, a matter-on-matter paradigm. You take a drug, it binds to a protein, or you have some surgical instrument and it interacts with the tissues. And based on these predictable patterns in technology development, we can predict that there'll be some future energy on matter paradigm in medicine. And I will argue in the course of this seminar that it's a terahertz medicine. The fourth question is, how does life work? This is a picture of what we call the yeast proteome, more specifically the interactome. The proteome is just all the proteins in the yeast organism. One can say the same thing for a human cell or a bacteria, etc. And the lines between the points, which are proteins or meant to represent proteins, the lines are interactions between these proteins. As you can see, this is reflective of the interactome of a living organism, a yeast. It looks like just a jumble of spaghetti. It looks very confusing. It looks very chaotic. And one wonders, how does life emerge out of this just random connecting between proteins? Now, what does this have to do with protein electrodynamics? But obviously, if these proteins have to physically bind to each other, then these interactomes can be very complex. But if they have some way of sensing their presence at a distance through energy, namely their electromagnetic manifestations, then there could be potential simplifications to this interactome. We're not going to answer that question definitively today, but I think you know, or I give you a sense of where the direction of some of the implications of these ideas are. So where do we go from here? What will be the future of medicine and healthcare? And perhaps more broadly, how can we better understand the fundamental mechanisms of life? So the story begins over 30 years ago as Dr. Wong introduced me. I had the great privilege of working with Martin Karplus and many other top scientists when I was an undergraduate. And he was one of the founders of what's called protein dynamics. Again, if you recall, the title of this webinar is protein electrodynamics. So obviously there's a relation. And when I was sitting at his desk, introduced as a young senior in college, undergraduate, where I did my senior thesis in his research group, he told me that proteins are neither solids nor liquids. They are something in between. And as a youngster or a college student, I was very fascinated by that. And that turns out to be true. And it's some explanation of what we're going to be talking about today. Proteins are neither solids nor liquids. They're something in between. So the second part of this webinar is on the fundamentals. We're going to go over what are proteins, the axioms of protein electrodynamics, protein dynamics, which is what Martin Karplus was a pioneer in, some scientific questions, what is terahertz, and moving towards terahertz medicine. So we have a diverse audience. Some of you may be doctors, some of you may be biologists, some of you may be electrical engineers, some of you may be in completely unrelated fields. So I'll give a little bit of introduction. Some of this, of course, may be quite familiar to you, so I apologize. So proteins, what do they look like? Well, you have two proteins here, myoglobin and basic fibroblast growth factor, obviously molecules in the body. And then here's a few more, androgen receptor that binds to testosterone and human growth hormone. And you can see they're very beautiful pictures here. But the key point is that proteins come in many different shapes and many different sizes. This is the contrast from DNA. Most of you are familiar, of course, with DNA and the double helix. Double helix is rather boring. I mean, it has genetic information, but structurally, it's just a helix, and it goes on for billions and billions of base pairs. Whereas proteins are like different personalities. As I said, they come in many different shapes and sizes, and these are just a handful of them that I've shown on this page. Then what do proteins do? Well, they do everything. They are the machinery of life. You have structural proteins, collagen, you have storage proteins like I showed you with myoglobin storing oxygen. We have transport proteins like the hemoglobin I show you that transports oxygen. We have hormones, we have receptor proteins such as the ACE2 protein, which is a receptor for the COVID spike protein. We have contractile proteins such as myosin and actin that causes the muscles to contract and defensive proteins like the antibodies that the vaccines we hope are stimulating, and finally enzymatic proteins with catalyzed reactions. So they do everything. So obviously proteins are both very diverse and they're very important. So here's an example of one protein. It's called the KCSA. You don't need to know really the details of that, but it's a protein that's involved in nerve potential, action potential. the signaling that the nerve cells do. So obviously it's extremely important for nerve signaling. And it's a potassium channel, potassium ion, and you can see these huge movements. It's opening up, and it opens up this channel for potassium to go through the membrane. And these huge movements represent protein dynamics. So what are the axioms of protein electrodynamics? Well, the main result of this, of these 5 axioms, I put it, or 5 assumptions, or truths, if you will, but facts, are that proteins emit and absorb electromagnetic radiation. If there's one takeaway from this webinar is this picture of a protein vibrating. If you're watching it on a smartphone, it might be hard to see. If you have a desktop, you'll definitely see that it's wiggling and jiggling. And we call this protein dynamics. And the first axiom, namely, is that proteins vibrate. That's the solid and liquid sort of transition that Professor Karplus was referring to. The second fact is that proteins are charged. They have positive and negative charges. And this is a protein, the acetylcholinesterase receptor, or acetylcholinesterase, not a receptor, but an enzyme. And it has blue and red on its surface, and the blue and the red are meant to reflect positive and negative charges, respectively. So the protein is typically overall neutrally charged, but there are a distribution of charges, or dipoles, on its surface. The third fact is Maxwell's equations, which are the equations that dictate that vibrating charges emit and absorb electromagnetic radiation. And therefore, the axiom is that proteins emit radiation and that they absorb radiation. And those are the axioms of protein electrodynamics. So let's talk about some of these steps. Martin Karplus and others taught us that proteins vibrate. This is the original Nature paper in 1977. And in 2013, many years later, he, Ariel Warshel, and Michael Levitt got the Nobel Prize for molecular dynamic simulations, of which protein dynamics was one of the major results. So let's give some examples of this. This is a glucosamine 6-phosphate deaminase. Let's see if it comes up. And this is a molecular dynamics simulation of glucosamine deaminase. And you can see the vibrations and so forth. And then we can go to another example, more zooming in. And you can see, again, we call this protein dynamics. So how do we know this, other than the molecular dynamics simulations? Well, there's experimental information, such as inelastic neutron scattering. This is Giuseppe Zacchi, another scientist I work with in Grenoble. And he actually measures the dynamics force constant, just like a spring constant. How stiff is a protein? How soft is a protein? And these are the various force constants, K, just like F equals minus Kx in Hooke's law with springs. And you have different Ks on different proteins and with different medium that they are dissolved in and so forth. So you can use neutron scattering, inelastic neutron scattering, to actually measure protein dynamics. And what are the frequencies? Well, using this neutron scattering spectra combined with simulation results, the molecular dynamics, this was done work by Jeremy Smith as well as Martin Karplus. This is the theory, and this is the experiment on myoglobin, one of the proteins that I showed you. And the peak frequency is around 0.45 to 0.6 terahertz, 10 to the 12th cycles per second, or 450 to 600 gigahertz. We'll talk about that in a little more detail. Obviously, as I mentioned, different proteins have different sizes and shapes, so those frequencies will be a little different, and perhaps quite different from different proteins. But this is the case that was seen both experimentally and theoretically, and correlation between the two with myoglobin. The bottom line is that these peak frequencies are in the terahertz and sub-terahertz range. So this leads to the very interesting concept that for proteins, the terahertz and infrared spectra can give information about their structure and dynamics. And using infrared for analyzing molecules is well established. Using terahertz is not so well established. So I'm going to contrast here the difference between the terahertz signal and the infrared signal when it comes to proteins. So infrared is sensitive to the small changes in the backbone atoms. So it's basically related to heat, just how the protein is jiggling at very high frequencies. But the differences between proteins, because these are all very generic motions related to heat, get washed out. And with terahertz, the differences between proteins, even similar ones, are quite apparent. And the large scale motions, such as in the potassium channel I showed you, are quite relevant for protein function, as opposed to the infrared motions, if you will, which are not so relevant to the kind of machine-like activity of the proteins. So we can compare them side by side. We call the terahertz the low frequency and the infrared the high frequency. The type of motions are large-scale motions in the terahertz and small groups of atoms in the infrared. So both of these spectra are sensitive to the changes. But if we want to distinguish between different proteins, as I argue, terahertz is much better. If we want to apply this to medical diagnostics on the basis of distinguishing different proteins, terahertz would be better. And the functional significance, as I mentioned, related to the action of the proteins is more related to the low frequency motions. And finally, if we modify those actions for therapeutic reasons, that will also imply that the terahertz is more appropriate than infrared. To put it in very blunt or high level terms, if we shine infrared light on something, it's like shining heat. You basically heat everything up. Everything will get hot. You might have some biological effect, but it's not going to be very specific. So let's talk, in the extreme, you'll just basically burn the target. So that's not good. So some scientific questions. Do different proteins vibrate at different frequencies? The answer is yes, actually. And can we identify different proteins based on their spectrum, the different proteins, for example, a cancer protein or a normal protein and so forth? These questions underlie diagnosis. And the answer to the second one is yes, but it's not easy for now. Protein anharmonicity, in other words, the softness of the protein and how it approximates a real spring, which we call harmonic, or not a spring, anharmonic. How significant is that? In other words, how tight are the frequencies? Well, it may depend. I don't think the answer is absolutely no, nor is the answer absolutely yes. And then on the sort of functional side, can one influence protein function by modulating their vibrations? The answer is unknown, although there are hints that this is possible. How far might the electromagnetic fields from a protein propagate? Maybe 1 to 2 millimeters. Could protein electrodynamics mediate specific interactive forces between proteins? This is unknown. And could proteins communicate even over a distance? Again, unknown. And the answers to these questions will be very important for applying to treatment. Now, we talked a lot about biology. Let's shift a little bit to the physics side. What is terahertz? Terahertz is the electromagnetic energies between the microwave and the infrared. We were talking about infrared earlier, so obviously it's somewhat close. In fact, microwave is on the low frequency side and infrared is on the high frequency side. And by way of definition, 1 terahertz is 10 to the 12th cycles per second, or 10 to the 12 hertz. Until recently, it's been very difficult to engineer this energy, and hence we call it the terahertz gap. And why is it difficult to engineer? Because if we want to produce radiation, there are basically 2 methods to do that in physics, in engineering. One is using electronics, and the other one is using photonics. Electronics uses unbound or conducting band electrons in metals, semiconductors, to create the electromagnetic emissions, whereas photonics uses bound or valence band electrons to create, through lasers and so forth, electromagnetic radiation that way. So unbound electrons on the low energy side, bound electrons on the high energy side, terahertz is right in between. So you kind of have to use electronic approaches in the least efficient way, or photonics approach in the least efficient way to produce terahertz radiation. But ironically, terahertz is all around us because it's emitted by the proteins in our bodies. It's emitted by all living organisms. And it's also strongly absorbed by water. So terahertz is not just protein electrodynamics is not just a frontier in medicine and biology, but it's also a frontier in the electromagnetic spectrum. All of you have heard about 5G, and 5G is in the tens to hundreds of gigahertz. And so it starts to approach this terahertz region. In fact, 6G will start to be in the sub-terahertz region. So that's a frontier in telecommunications and electromagnetics and so forth. So this is a chart of power and frequency. The red techniques are the photonic side. The gray techniques are on the electronic side. You can see terahertz is right in the middle. You can see the logarithmic energies or powers are much lower. It's kind of a gap, as we mentioned. So what are the natural sources of terahertz radiation? I mentioned engineering-wise, it's very difficult. Well, this is where the Immanuel Kant quote comes in. Two things fill the mind, the starry heavens above and the moral law within. So the starry heavens above refers to the cosmic microwave background. Now we're getting a little bit into astrophysics. In fact, a lot of terahertz research comes from astrophysics. Why? Because the residual of the Big Bang, called the cosmic microwave background, actually is a black body. In other words, it has a distribution of radiations in which this tail, which is colored here or shaded in, is in the terahertz. And about 10 billion years ago, as the universe was cooling down subsequent to the Big Bang, the peak was actually not in the microwave, that's why we call it cosmic microwave background, but the peak was in the terahertz. So if you were an astronomer 10 billion years ago, you would be referring to the cosmic terahertz background. So it's coming from the starry heavens above. That's the natural source of terahertz. And then, as I mentioned, it's coming from the proteins in the body. It's part of life. It's the moral law within. It's life itself is a natural source of terahertz radiation. Now, this can be leveraged for practical purposes. The New York City Police Department uses a T-ray machine, detects terahertz radiation, a high-frequency electromagnetic natural energy emitted by people, can penetrate many materials. So this is a standoff passive detector, and this is the green, just like in a night vision goggle, is a terahertz emitted by the person, not infrared, but terahertz. And a gun here is not composed of protein, it's composed of metal, will not be emitting the terahertz. And by virtue of the contrast, they say, okay, that person has a concealed weapon or a gun. Now you might say, why don't they use infrared night vision? Well, remember, that's related to heat. So if you have a gun in a holster here and it gets warmed up by your body, there won't be any contrast. The whole image will be green, picking up the infrared. And airports use this in millimeter wave scanners. So this is actually a sort of primitive form of terahertz scanning. It's a much lower frequency. It's in the millimeter waves, but it's a similar sort of concept. So there are two technical challenges. One is producing those terahertz sources. Remember, we said we have the terahertz gap here as the power decreases. And so sufficient power and spectral resolution, tight frequencies. And then water absorption is also an opportunity and a challenge. So we talked about X-rays in the beginning of this webinar and MRI and so forth. These rays pass through the body, in the case of MRI radio waves, but terahertz does not. It is absorbed by the body and it doesn't go straight through. So we're not going to have, certainly not in the foreseeable future, terahertz scanning machines that go through whole body scanners. It penetrates about 1 to 2 millimeters, maybe 2 to 3 millimeters, depending on the circumstances that I'll describe. And that is predominantly due to the water absorption. And we'll talk about that in a little more detail. So what are the principles of terahertz medicine? Well, we can use this as a form of diagnosis, both structurally to see imaging based on water, protein content, and so forth, as well as spectroscopic, combined in a label-free fashion. The spectroscopic to pick up specific proteins, not just general structure, but functional studies. We can also use this as a kind of energy-based protein-specific therapy. And this is what I was referring to, the future of medicine here, being an energy on matter approach. Now, I should contrast this. We obviously have energetic approaches in medicine. Everyone is familiar with lasers that do things, whether they be surgical cutting with the lasers, even something as primitive as Bovi electrical device to burn tissues. We have, of course, radiation oncology. It should be noted that these energetic approaches do not interact biologically. They actually irritate, burn, destroy the target tissues. In other words, they act through a physical mechanism. You don't have an energy in radiation oncology gamma ray that activates one specific protein. The way to think of this is this future energy on matter is not what I say is a physical mechanism like high intensity focused ultrasound or radio frequency ablation or gamma rays or whatever. It's a kind of drug effect. In other words, it's protein specific, just like aspirin or ibuprofen or an antibiotic. It's a protein specific effect, but it's delivered energetically rather than mechanically. So the three principles of terahertz medicine are resonance. There should be some target, protein target with certain frequencies that resonate. They should be localized. So we don't irradiate the whole body necessarily. We will focus on certain tissues, so things like cancer and whatnot, certain localized lesions. And of course, the targets have to have some functional significance. We might use lasers, for example, to do collagen stimulation in the skin. But as I mentioned, that is a physically destructive mechanism. So the collagen is stimulated through the destruction of the subcutaneous tissues, and the collagen is serving a structural role, not a functional role. So the optimal targets in terahertz medicine are proteins that have significant charges and dipoles and large-scale motions involved in their function. We call them electrodynamically active. And that's why I said it depends. Some proteins might not have such a signal, and others would have a larger signal, which by the laws of electromagnetism will be based on how big are their movements and how big are their charges. So it turns out that these putative electrodynamically active proteins are very important proteins, allosteric regulatory proteins, which are often the target of drugs, ion or other channels, like the potassium ion channel we saw, signal transduction proteins, the receptors, transcription factors, and so forth. So this KCSA is likely to be electrodynamically active. It has big motions, it has lots of charges to accommodate the potassium charges and channel in its channel, and so forth. Albert Einstein is once noted to have said, future medicine will be the medicine of frequencies. So now let's talk about some specific research results. I'll be talking about the protein terahertz spectroscopy of myoglobin and hemoglobin. We saw myoglobin earlier in the context of the neutron scattering results with Jeremy Smith and Martin Karplus. We'll discuss some other studies in the Open Innovation Program that I worked while I was at Samsung, the terahertz imaging of cancer, terahertz imaging of Alzheimer's disease, two-dimensional terahertz spectroscopy, integrated terahertz sensor, and some further conclusions and technical challenges. All this work has been done in collaboration with other universities, Hanyang University in Korea, Ohio State University, MIT, UC Irvine, University of California, Irvine, and other institutions throughout the world. So one important concept that I want to start out with is that whenever we probe matter spectroscopically with electromagnetic wave, there are two ways we can probe it. Well, there's a reflection, there's transmission, all of you are aware of that, but two ways that we can probe it in terms of process. One is called time domain spectroscopy or time domain measurements, and the other one is called frequency domain measurements. In time domain measurements, we irradiate the sample with a whole dose of multiple frequencies and observe the results. In frequency domain measurements, which is the more conventional way, we irradiate with a specific frequency and probing at individual frequencies. Most measurements, especially because the devices are off the shelf in the terahertz realm, are done in time domain measurements. And I'm not going to go into the reasons why. That's the dominant, by far dominant measurement method, but that's where many of the experiments will be done. Now, as I mentioned, time domain means a whole range of frequencies. So MRI works this way. You put the patient in the MRI scanner and you put a wide range of a pulse, which results in a wide range of radio frequency energies. And then you see that pulse activate various proton spins in the body. They relax, they spread their energy, and then you can reconstitute an image from that. It's a little bit complicated, but it's quite straightforward. It's very elegant. You just have one pulse or a set of pulses, and you can get a lot of information. In the body with terahertz, those pulses will start to mix with each other. And if you put in a whole range of frequencies, you'll get out a whole range of frequencies that have interacted. We call them nonlinear and they're interacting with each other. So that becomes a big problem. So one of the key points that I'll be making is we need to do more of these frequency domain measurements, which has been a great challenge. And I'll explain a little bit more what I mean by that. So the first experiments I want to talk about are with myoglobin and hemoglobin. Myoglobin is an oxygen storage protein. Hemoglobin is an oxygen transport protein. So they're very similar. And we did this at the Pohang Accelerator Lab in Korea with Sungam Ryu of Hanyang University. And this is the setup. It's a femtosecond laser, so it has a very tight pulse. And by the Heisenberg uncertainty principle, as you know, a very tight time is going to be inversely related to a spread in energy. And so we create a great spread in energy, in other words, a time domain experiment. So we found using hemoglobin, simple methemoglobin, and comparing to air, that there was a difference in the spectrum between hemoglobin and air. We saw a high frequency broad absorption, a specific absorption around 1.3 terahertz, and another one around 0.8 terahertz as compared to the air control. And then we did a further experiment comparing myoglobin and hemoglobin, and again, time domain spectroscopy. And we had three samples, one with bovine, which is cow hemoglobin, one with myoglobin, and the other one with human hemoglobin, red, green, and blue respectively. And you can see that there is some difference in undulation. And we see a difference between myoglobin and hemoglobin. We see a species specificity. Remember I said cow and human. So cow is red and human is blue, and you can see they're actually opposite. So even though the proteins are very similar, they have a slightly different terahertz spectrum. And then we see a potential Stokes shift or emission. In other words, negative absorption is emission. The protein is absorbing at high energy and spitting out terahertz at low energy. Then we did things with sample thickness to see if some of this was related to artifact. And you can see at 0.5 millimeter sample thickness, which approximately is related to the wavelength of these terahertz energies, we see artifact, but some of the peaks that we see are not related to artifact. That means it's a real resonance. Now the results are comparisons. So we saw about 450 gigahertz here with myoglobin. We also see with myoglobin 450 to 600 gigahertz as well. So there's some correlation between those results. So in conclusion, we have broad yet specific low frequency absorption around 450 gigahertz, along with other spectroscopic features as I highlighted. We saw differences between species, between the human and the bovine. And we saw similar features of this globin fold. These are similar proteins, they're not the same, of course. And we saw a possible stimulated emission or Stokes shifts, so proteins as terahertz emitters. Now, what's interesting is many of you that have experience in infrared spectroscopy or NMR spectroscopy will look at those spectrum that I just showed you and be duly unimpressed. It's not very sharp. It looks very broad. But the fact that there is some features is extremely important and very promising, as I'll talk about. So it's not completely featureless. And in fact, sharp protein resonances exist. This is work out of the University of Buffalo, another lab with Andrea Markels with lysozyme. And you can see a very sharp resonance for lysozyme of 1.5 terahertz. Now, these degrees here are not temperature degrees, but actually the angle between a polarized terahertz beam and the crystal, specific crystal face. So this is a crystal of the protein, and which makes sense because the dipoles of the protein are lining up in a organized, regular fashion in the crystal. So you get a very sharp peak. And also follow-up studies that Professor Markels did in their group is that with motions and function of the protein, or I should say with different states of the protein, different functional characteristics of the protein, these motions change. So this is the protein has an approximate hinging motion of the overall transition dipole. When you have an inhibitor of the lysozyme is a protein that breaks down sugars. It has a very different motion, a twisting motion, different frequencies and so forth. The transition dipole shifts. Proteins can also emit terahertz. This is bacteriorhodopsin at 0.9 terahertz. And protein dynamics is also related to protein function. So this is another study, simulation study by Martin Karplus. This is a cancer protein called SARC. Those of you who are molecular biologists will certainly be familiar with that. So SARC is a protein that, or a gene, we call that an oncogene that in the wild type doesn't cause cancer. In the mutation, it does cause cancer. And this red image is the heat map of the motion. It's meant to give a high level view of this motion. You can see that cancer proteins are different than normal proteins. So while I was at Samsung, I created a kind of virtual institute, open innovation around their GRO program, which is Global Research Outreach. It was an open innovation program that gave grants to labs around the world to work with Samsung researchers. And so some of those grants, we worked in this kind of organized way around terahertz medicine, or I should say protein electrodynamics, so forth. So we had 4 major projects, one with diagnostics, medical imaging, another one with medical spectroscopy, another one with therapeutics, and one with the engineering side, with the Ohio State University, MIT, Southampton, and UC Irvine, respectively. And I'll talk about these 3 areas. The University of Southampton eventually did not work as a project because we couldn't get the instrument to produce those very sharp frequency domain measurements. And I told you it was very difficult. So at Ohio State, we published several papers coming out of this work with the Kubalai Sertel and Niro Nahar. One of them was with cancer, and we basically saw differences between normal and cancer tissue. Another follow-on study we did with Alzheimer's disease, and these are pathological samples, by the way. And Alzheimer's, you know, has amyloid deposited. So the amyloid is deposited and ultimately leading to dementia. Our hypothesis was the amyloid, which is regular aggregations of proteins, might show up in a terahertz spectrum. So we did, again, time domain spectroscopy, reflection mode. We looked at samples pathologically, histologically, and we compared to histopathology. We also did some simulations, which I'm not going to talk about. Again, experimental setup. This is not a femtosecond laser, but actually essentially a off-the-shelf unit by TeraView. Sample preparation was very important to regularize the dimensions because the wavelength of terahertz radiation is quite similar to the wavelength, or I should say the dimensions of our sample holders and so forth. So we wanted to avoid that kind of artifact that I alluded to earlier. And these are some of the initial comparative images of the hippocampus. This is a gray matter, and you can see white matter here. Gray matter is the cells, white matter is the axons. And to make a long paper short, we saw differences between control and Alzheimer's tissues. So in summary, we saw doing different kinds of analysis, spectral analysis. We saw these differences, particularly in the white and the gray matter ratios. So these are the Alzheimer's disease samples, are what we call terahertz image contrast percentage, and these are the control samples. So what are the conclusions? A strong correlation between Alzheimer's disease and terahertz image contrast, particularly in the white matter. We want to refine the technology. Additional applications such as multiple sclerosis and other myelin disorders, because it is white matter, seems to be something related to the white matter changes. And continuous wave techniques, in other words, frequency domain, we think could be even more useful. Another study we did to help answer this question, can we identify different proteins based on their spectrum, is 2D terahertz spectroscopy. This is with Keith Nelson at MIT, and we submitted a patent, which was granted a couple years back, for using 2-dimensional spectroscopy so we can separate out those frequencies from the more complex spectrum. And then with Payam Haidari, a very prominent semiconductor physicist at UC Irvine, we helped work on a silicon-based terahertz frequency synthesizer, integrated source and sensor. And it wasn't under the GRO, but another Samsung project was also with the University of Texas, Dallas, with Dr. Kenneth O in the Department of Electrical Engineering. Same thing, a chip that has an integrated source and sensor. The concept being we could have handheld, inexpensive devices. So finally, can one modulate protein function via terahertz? As I mentioned, the Southampton experiment aimed to answer this question, and we could not get the device, the frequency domain continuous wave device, to work. But there's been recent studies just earlier last year These are actin filaments of the terahertz pulse. Actin is a protein involved in muscle, and you could see disruption of those filaments unrelated to heat. Still open question. So the overall conclusions from this research are that terahertz interacts with proteins, definite signals are observed. Mostly these are in the sub-terahertz range. Continuous wave, tunable, or frequency domain spectroscopy, which should be better able to detect, and perhaps our MIT results in the patent can be used for 2D terahertz spectroscopy. Normal and pathologic tissues can be distinguished. Demonstrated applications in cancer and Alzheimer's disease. We can use this for imaging, and on the continuous wave side, spectroscopy. And the technology can be, that we think would be ideal, is high power, pulsed continuous wave or multi-frequency in the sub-terahertz range, and miniaturization, as I showed you, via silicon-based CMOS platforms. That's why I said this is of particular interest to CREST and some of its stakeholders. So as I mentioned, terahertz does not penetrate into the body because it is absorbed by water. Now, those of you might have noticed that water is not a big molecule like proteins. So you might say you are arguing about proteins absorbing terahertz, and then you have these small water molecules. How could that be? Well, it turns out that the water that is absorbing terahertz is not individual water molecules, but the whole hydrogen bonded network of liquid water. And it's that hydrogen bonded network, effectively a macromolecule, much more looser and more disorganized than a protein, of course. That is what is absorbing terahertz. So we're not really being absorbed by individual H2O molecules, but by this whole network. If you think about it conceptually, the protein macromolecule is competing with the water macromolecule. So I propose 4 methods to solve the water penetration problem. First one is to use the sub-terahertz region. Many of the papers that have indicated disappointing results with terahertz have focused on the higher frequency range. And this is a graph that shows that there's more frequency, higher frequency, more absorption. And in fact, that sub-terahertz range that is relevant to the biomedical applications that I've been pointing out has less water absorption. It's not zero, of course, but it's less. So there's more hope, let's put it that way. Then we can also use what are called water windows. And this is well established in the microwave area, where you have areas of higher transmissibility in water. And this is still not completely clear, but clearly, or certainly, if you irradiate with this time domain, whole swath of frequencies, you will be less able to take advantage of these water windows than if you have specific or frequency domain measurements. So tunability, which we weren't able to do in Southampton at the Optoelectronics Research Center, affiliated with the university, and it's very difficult to do, but if we can achieve that, which is possible with these chips, then we can leverage the water windows or areas of greater transmission to reach deeper into the body. A third approach is pulsed radiation, not femtosecond pulses like I talked about, which create that Heisenberg spread, but longer pulses, albeit still short of 10 picoseconds or so, that go through water without activating all those hydrogen bond networks. So in other words, it's pulsed quicker than the water can respond to it. And that's to minimize, as I put here, water relaxation effects. And the last approach is, of course, high power, Beer-Lambert and so forth, just we need higher power sources. So based on the biology, back to the physics, as I mentioned, we have the electronics regime and the photonics regime. And I've summarized here the 4 basic approaches: solid state, vacuum, direct lasers, and electro-optical conversion. Now, because the only one that creates tunable radiation is the solid state, plus it's coming from the lower frequency side, I believe that the solid state CMOS approaches or related approaches, semiconductor approaches, again, this is why CREST is such an interesting potential partner in such an endeavor, that will probably be, of all these techniques, the most promising for biomedical applications. Again, because it's lower frequency and it produces that kind of single frequency as opposed to these broadband, we call it pulses. So what is the future of medicine? Well, it's going to be this energy area, as I mentioned. So let me go to the last 10 minutes or less with some applications. I'll go very quickly through these because these are not hard research results, but more like ideas and speculation and so forth, but potential applications. So we'll start with why. We'll talk about new medicine. What are the potential applications? I'll discuss a experiment, a terahertz light switch, talk about cancer, antibiotics, drug screening, protein-protein interactions, new paradigms for COVID, why now, the quadcopter, and it's more than just technology. So we fundamentally need, as I mentioned, new approaches to diagnosis and treatment. We mentioned that medical imaging is stalled with a lack of specificity being a key limitation. Biopharma is not as easy as it used to be. Unsustainable cost. Technology evolves, and I think it's inevitable that we will have an energy on matter approach. Just like in the technology of war, we don't send people in with fists to punch the enemies. We have weapons, and those weapons have evolved over the many centuries. And I'm not saying that's a good thing. It's just the reality of life. But we don't work with the weapons that humans did thousands of years ago. Technology has evolved, and the same obviously can be told for medicine. So energy on matter will be the future paradigm of medicine, offering greater specificity, more non-invasive, greater effectiveness, lower cost, more rapid therapy development, and a convergence of medicine and surgery. So what is this new medicine like? It's not just this protein electrodynamics. This is Time Magazine. Just a couple of years ago, why it's time to take electrified medicine seriously. Google spinoff with pharma to treat disease through what they call electroceuticals, Galvani Bioelectronics. There are lab groups around the world that are starting to grow, and you can see this is sub-terahertz, protein, terahertz, control function, spectroscopy. So these are a lot of buzzwords or keywords that are increasingly developing around this area. What are the potential applications? We have cancer. Many cancer drugs work on proteins. If we can influence those proteins, such as this microtubule that's involved in cell division, that's a definite possibility. Antibiotics, neurological, wound healing, and more. It's a real platform technology. So one elegant experiment that I envision is what I call a terahertz light switch to control bioluminescence. Most of you are familiar with bioluminescence. For example, the glowing jellyfish and then the fireflies. That's delivered by a protein called luciferase. That protein is activated, and it's activated chemically. But if we could have a terahertz ray that actually activates it, you switch on the terahertz machine at the right frequency, turn on the luciferase, and you get optical light or visible light appearing. It may not be an application with great practical significance. You could get very interesting light shows, of course, but it would be a very powerful representation of the concept of turning on a protein or turning it off from a distance by using some form of electromagnetic radiation, in this case, sub-terahertz or terahertz. We could do this cancer in microtubules, as I mentioned. The most powerful anti-cancer drug is called Taxol. It's used less and less because it has a lot of side effects. It has a lot of side effects because it affects growth of these microtubules of all dividing cells, not just cancer cells. So if we can have this kind of effect, but zoom it in almost surgically, but not using surgery, but zoom it in on the cancer tissue electromagnetically, we can have the power of Taxol, but also its specificity anatomically. And imagine also antibiotics. Now, antibiotics are, right now, we've been in this situation with COVID, of course, which is a virus, and so there are no antibiotics for COVID. And we don't take bacterial diseases so seriously because we have antibiotics. But I can tell you this, if you have a bacterial disease in which there is total antibiotic resistance, COVID will appear like kindergarten, as they say. In other words, we will have a complete catastrophe if we have what's called the post-antibiotic era being apocalyptic. And so we need antibiotic, and we need to address the antibiotic resistance. Now, the problem is the target of the antibiotics are proteins in the bacteria. And the way they evade or become resistant is those proteins mutate. And we are seeing this already in COVID, some mutations and whatnot, and the vaccines work or they don't work. And they have to adapt to that protein, which means you have to design a new vaccine. You have to design a new drug. Everything has to be done from scratch, or at least we have to redouble the effort. Whereas if you have a mutant protein that has a different frequency, designing a new electromagnetic antibiotic would be amount to basically shifting the frequency, which means there would be some work involved, but it would not be developing a whole new drug from scratch. So we have what I would call resistance-resistant antibiotic therapy. So drug screening, if we want to find these drugs, we could do, there are drugs screening machinery and robotic systems and so forth. Instead of sprinkling with drugs and testing different drugs, we could do testing of different frequencies. And this is the Institute Pasteur in Korea, a potential project that we've been considering. And similar sorts of advanced technology for protein-protein interaction affinities. So what is a virus? Obviously, everyone is very well aware. It's a genetic material contained within an organic particle that invades living cells, uses the host metabolic machinery to produce new virus particles. So the SARS coronavirus 2 virus has three parts. It has, from the inside to the outside, nucleic acid. It has the lipid membrane, and it has the spike protein. Nucleic acid is genetic material. The lipid envelope is related to the environmental viability. And finally, the spike protein determines the target, and that's what's blocked by antibodies. The virus is not an independently living organism. So there are only two ways to get rid of the virus. One is to physically destroy it. The other one is to clear it by the immune system. So there are not really antibiotics that can kill it. But physical destruction is one approach. Now, one application is handheld thermal scanner, which everyone's seen in the airports and in public spaces and so forth, a handheld COVID scanner. So instead of picking up infrared radiation from the forehead, we pick up specific frequencies related to viral proteins. And we're doing a project with Middle Eastern Technical University that has a graphene and surface plasma resonance with terahertz to see biosamples there. So obviously there are medical as well as military purposes. One can modulate protein function electromagnetic for medical purposes. Then one can also do it for military goals. So there is a lot of research, most of it's secret, of course, that we're not supposed to know about, using this sort of concepts for military purposes. That's not the purpose of today's talk, of course, but I just wanted to give that by way of background. So terahertz physics has been a challenge, but why now? There's a growing interest with more papers and so forth. It's becoming mainstream. We have better performance and miniaturization, as I mentioned, and very importantly, decreasing cost. So we can imagine a Star Trek tricorder. Star Trek was, the Delvin show was an inspiration for many technologies, such as mobile phones, flip phones, and a tricorder was a medical instrument. But we could have, and that was focused on diagnosis, we could even have something that does some therapy. So I call that a quadcorder. Now, this is more than just technology. There's a lot of ethical issues and social issues and adoption and so forth. So I've actually written a novel called Waves. It's available on Amazon that explores this technology, not just in the technical setting, not just in the research that I described, but the broader societal aspect. And as a matter of a thriller, if you will, this tug between the military and the medical side of things. So for example, there's a section where they use this voltage-gated potassium channel as a target in chapter 19. So some closing thoughts. In summary, protein molecules, the machinery of life, and the targets of most drugs are not solid, but are vibrating. That's what Martin Karplus taught us. And we call that protein dynamics. Proteins have charges, positive and negative. So therefore, proteins can emit energy and they can absorb energy. This is a fact. And we call this protein electrodynamics. They're like radios. And like radios, they can be detected and modulated. But this gives rise to an entirely new approach of diagnosis and therapy, respectively, which we call Terahertz medicine. And the key precepts of this are described in the book, as well as some of the other research that I talked about. So I've spoken around the world this topic in the Americas, Europe, Australia, and of course Asia, and now today with collaboration with Crest. And one of my heroes is Isaac Newton, and most people obviously consider him the father of modern physics or the founder of modern physics in his Principia, the Newton's laws and mechanics and so forth, and gravitation. But he was very interested in biology, and in his General Solium at the end of the Principia, the final words, he talks about the laws by which this electric and elastic spirit operates in terms of the nerves and the muscles and so forth. And he wasn't aware of proteins, of course, but I think the way he talks about electric and elastic spirit is a very nice way to encapsulate this. And of course, there's Richard Feynman. Most of you who are physicists would be, of course, well aware. And he famously wrote in the first set of his books, Lectures on Physics, everything that living things do can be understood in terms of the jigglings and wigglings of atoms. Then I had the opportunity to give a short seminar. Many of Professor Karplus's students did at his celebration symposium in San Francisco. And after my seminar, I asked him, what do you suggest? And he said, I would do the experiment on an enzyme. If it works, it would be significant. Now, I wanted to mention that technology often is not pretty in the beginning. So you saw some of the spectra, you looked at some proteins, you said, oh, it's not penetrating the body. So there's a lot of problems, let's give up. Well, you know, in the beginning, technology is not always pretty. You know, the Wright brothers didn't give up. And then the people after the Wright brothers didn't give up. And so from this flimsy bicycle with wings, we got, of course, jet planes and to the moon. We're going to Mars and so forth. Even just today, landing and coming back from Mars. And that all began with this. So in the beginning, technology is not always pretty. So exactly 1 hour. We have time for questions. Thank you very much. I should also add that I can be reached by email. I am on LinkedIn as well. You can just search for my name on LinkedIn, and happy to connect there as well. So thank you very much, and open to entertain questions.
Thank you, Dr. Gurel, for your very interesting and philosophical presentation. I never thought that the molecule can dance so beautifully. And also you
That's the best
showed
way.
that the Star Treks, and I can't imagine these things have existed for like, since Big Bang, but we still haven't utilized it in medicine. Maybe it can be the next new petrol in medicine, and we can utilize it in diagnosis, in treatments, and so on and so forth. And I'm sure
Yes.
we are having questions coming in from our Q&A sections. Maybe we can start addressing Mr. Jeffrey asking if we are going to embark this in Malaysia, how are you going to suggest, like, you say are the ones you would recommend to like start collaborating in Malaysia?
Yes. First of all, Dr. Wong, I want to thank you for the very eloquent way you summarized. You said the dancing molecules and all that. You said it better than I did. So thank you for that. It's actually quite fascinating. So back to Jafri Ibrahim's question, plenty of opportunities for innovators. And then his second question, which is related to expertise in multiple diverse areas, what would be the composition of the team, specifically experts in what particular areas? Now, this is very interesting because one of the reasons why this technology has not been implemented widely, there are technical barriers, but one of them is effectively a cultural barrier. And what do I mean by cultural is that you require, as Jafri Ibrahim notes, many different specialties. There's a reason why I pointed out the Big Bang and astrophysics, because in reality, a fair bit of terahertz research comes from astrophysics, right? And so if you want to do medical, I mean, think about the scientific field that's most furthest from biomedicine. It'd be like astrophysics, right? So my point is you definitely need an extremely diverse group of scientists and engineers to come together. Now, one reason, yeah. So specifically, you need doctors, you need protein chemists, you need electrical engineers, high-end electronics engineers, you need some physicists and material scientists perhaps, and of course device manufacturers. It's a very diverse area. Now, one of the reasons why I think CREST is so uh, fascinating in this regard is CREST intrinsically collaborative research, bringing together different stakeholders. CREST is not the only organization in the world that brings together different stakeholders, of course, but there are not many of them that really do this across different areas, the business side, the technical side, and so forth. So while CREST, much of its work has been done in the semiconductor industry, which is quite diverse, we would do that to the next level, if you will, to answer Joffrey's question more directly. We would also bring some medical and biological scientists into the mix. But yes, the key challenge to me, as I see it, is not the technical challenge, which always is a challenge. The key challenge is to bring together the network of all these different scientists under some umbrella. This was also kind of the point that I mentioned with my virtual institute that I talked about with the Samsung GRO, is that was not a building, that was not, a specific institute. It was a virtual institute where we had Ohio State, MIT, Southampton, UC Irvine, and of course the Samsung researchers all kind of working together. There was obviously some money involved, but we were bringing all those pieces together.
The next question is from Mary. She's asking whether we can get some insight from ancient medicine which utilize chakra theory. Since I think you have a slide talking about Albert Einstein, and then there is this utilizing the next phase of medicine is using the frequency. So can we take insight from our ancient knowledge and try to reinvent how are we going to explore the terahertz in medicine?
Sure. Well, I think this is, I don't talk about it too much in my presentation, which is more grounded in biophysics and so forth. In other words, I don't have any slides about Oriental medicine or Chinese medicine or ancient medicine. It goes by many different names, of course. But I think it's a similar concept. But obviously, I'm aware of it. And I'm not an expert in these areas. But my intuition is that this protein electrodynamics, which is very much based on biophysics, which the ancients may not have known about, obviously, proteins, but certain aspects of it may overlap with these elements of phenomena that have been observed in Oriental medicine. As I said, I'm not an expert in this, but I would not be surprised. I wouldn't say it explains everything, and I'm not saying that everything in Oriental medicine is absolutely established in biophysics either, but there is likely to be some overlap. And I think that could be another interesting area. So as Joffrey Ibrahim mentioned, what would be the mix of experts that you would bring in? Potentially some Oriental medicine experts, particularly those that are more scientifically oriented, could be part of that mix to explore, where some of the established techniques could be improved upon. For example, I actually published a paper with some colleagues, not in terahertz, but with the electromagnetic effects of some nano patterning of the electrodes used in acupuncture.
Oh.
And so those influence, or at least postulated to influence, certain electromagnetic properties and so forth. Now, as I said, that was not a terahertz medicine paper. I was just helping their team, and I was involved in formulating the concepts and putting it together and so forth. But one reason, I don't just write random papers. It was intriguing to me is that there was this electromagnetic biophysical component to it. Next question.
I think our question is you have answered it before, the mixture of the team. So maybe do you mind to share a bit of your own experience, how you advise them to start?
Well, we didn't go too much into my background, but you introduced me very nicely. But just a little bit more. So I've been involved in innovation, and I teach innovation, and I've worked with startups. And I actually think that the whole field of innovation is progressing to, I don't want to simplify, but a whole area of what we call open innovation, where you have networks of different ideas coming together. And one reason why I say this is that if we look at the fourth industrial revolution, many people have talked about the fourth industrial revolution. There is no defining technology for the fourth industrial revolution. The first industrial revolution was largely around the steam engine. The second industrial revolution was largely around electricity. The third industrial revolution, if we kind of call it these things, was around computers. So what is the fourth industrial revolution? Some people might say AI. I would disagree. Some people would say robotics. I would disagree. Some people would say, 5G. I would disagree. Why do I disagree? Because robotics alone is useless. AI alone is useless. 5G alone is just radiation in the sky. It's the convergence or combination. So in other words, the fourth industrial revolution is not defined by one technology. It's defined by technology convergence. In other words, the whole paradigm of innovation in our current era is defined by convergence of technologies. And that will also hold true for this terahertz area. So my experience is that if we want to ride the mega trend of innovation, we need to create a convergent concept where we have the astrophysicists, the biomedical scientists, the oriental medicine, the business people, all that working together virtually. And we can do that more with Zoom and all that, more than we used to, more than the virus COVID has forced us. So we need to create that kind of an open innovation institute / incubator. Now, I should also say that this will also change the model of startups. Isolated startups around one technology, I think, will become increasingly obsolete. The innovation will not be in the startups. The innovation will be in the ecosystems. And startups will be kind of a side manifestation of that. So business incubators and so forth, innovation incubators, instead of focusing on startups, should really focus on the ecosystem. And CREST is also an ecosystem, if you will, generator, albeit in a different area. So I think some of those learnings and some of those mechanisms, I think, can be very well applied to new initiatives, such as in protein electrodynamics and terahertz medicine.
Yes, so now singularity should be extend to multiplicity. So everything can work together and in order to advance further. I think our next question is about cancer technology for cancer applications. Can this also be applied on medical disease such as diabetes mellitus and blood disorders?
Yes, so as I mentioned, it's a kind of platform. So pharmaceuticals, drug therapy, is a platform, right? How does that platform work? The platform works by identifying a target. There's a technical name for that in the pharmaceutical industry. It's called lead generation. But identifying the target, and in most cases, it's a protein. We have gene therapy, we have mRNA drugs, and so forth, antisense that work on other areas. But in general, 99% of drugs out there, more than that, act on proteins. Those are the targets. What do they do to the proteins? They either activate them. Again, I'm simplifying, all of pharmacology, but they either activate the proteins or they inhibit the proteins. And we have technical names for that, agonist and antagonist. So that's the platform of pharmaceuticals. So they, or they replace those proteins, like insulin in the case of diabetes. Because in some forms of diabetes, mellitus, the insulin is low or not active. So if you take that same platform of the protein targets, but instead of using a physical piece of matter, namely a drug, to influence them, you use electromagnetic radiation, then effectively it's the same concept. So my point is that any target that's affected by a drug can also be potentially affected by this approach. So let's look at diabetes, for example. Lack of insulin in the body. What does insulin do? It binds to the insulin receptor to absorb glucose and so forth. So the way we pharmaceutically treat that is we inject insulin. We give the patient insulin, or the patient gives themselves insulin. It's become fairly routine. But if you had some sort of device, say you position over the liver where there's a lot of glucose receptors and so forth, and it turns on the glucose receptors, it turns on the insulin receptor in the liver electromagnetically, you don't need the insulin. It does the same job as the insulin, right? It does the same job as the drug. That's a little extreme example, but I'm just trying to frame this. So then someone mentioned about blood disorders. It's the same thing. So any target, protein target that's addressed by a drug could potentially be addressed energetically. I do think some diseases will be easier than others in this technique. For example, we mentioned that terahertz doesn't get into the body very deeply. So this example of pointing at the liver might be quite fantastical because you got to go several centimeters deep, right? But for skin diseases, I think the applications are, we can see them in the very near term. We're talking soon. For others, it may take longer. So even though the platform is theoretically accessible across the board, some will be easier, some targets will be easier than others.
Yeah, thank you. I think this means that we still can maybe we can start in exploring this technology in dermatology field since it's like more superficial compared to the
That's
other.
right. Yeah. So like any other startup or any other
aesthetic field.
Aesthetics, exactly, cosmetics and so forth. I think you want to be strategic about it based on the capabilities and so forth. And I definitely do have ideas about that. And I think that is indeed how things will play out. You're not going to conquer all of medicine all at once. But theoretically, it's possible.
Our next question is from Shash. He did mention that, okay, very interesting, Dr. Gray, convergence innovation is the way forward. And from Kamaleshwari, can I ask you a basic question about the COVID vaccination? Just would like to know how long does it take for our human body to build the immunity protections after a vaccination?
First of all, we should consider the process more generally. We have active immunization or passive immunization, or actually natural immunization or active immunization. Natural would be just getting infected. Artificial would be through a vaccine. And the process is quite similar, obviously, to generate a secondary immune response. So the problem with answering your question definitively is, what do we mean by the secondary immune response? Roughly speaking, there's an antibody immune response, which is the most important one that we look at. But the other one, which might be more important for longer term immunity, is the cellular immunity response, T cells, which you may have heard about, etc. So typically the antibody response occurs a little bit faster, maybe in a matter of a week or two, whereas the cellular response takes a longer time. So these time frames vary, and different diseases as well as different vaccines stimulate different parts of these to varying extents. So for example, in the current COVID vaccines in general, we know, and in fact, that's part of their approval, is that they generate these antibodies. But they vary in the degree to which they generate the cellular immunity, which takes longer. So there's been a controversy whether the immunity lasts for a long time. And if we just generate the antibodies, and again, it depends on the class of antibodies, so it's a little more complicated. But and that also has different time frames. So if we just generate antibodies and not the cellular response, we may end up having a limited immune response. So the answer to your question, there's no number like, okay, it's 2 weeks or 3 weeks, because it depends on what you define as generating the immune response. But I would say as a general answer, if we're talking about immunoglobulin G, IgG, the major antibody in the blood, we talk about 2 to 3 weeks to generate that secondary response. Again, that's going to be a curve. You might have 50% of the secondary response, 100%. So, so that might take a longer time if you're talking about 100%. But roughly speaking, we're talking about a matter of a few weeks. To answer your question very simply, but to emphasize that there is no simple answer to that question.
Okay, thank you. I think our next question will be about COVID-19 again, but this time they are asking whether we can utilize the terahertz dynamic to identify antigen protein for different type of like mutated virus.
Yeah, so I think that could also be used to instantly, in real time, detect a mutant, virus. Of course, it depends on the precision and the technology, but in principle, you could do that. Why is it in real time? Because you're picking up an electromagnetic signal. PCR is an actual reaction, or actually it's millions of reactions, right? The polymerase chain reaction. It takes 4 hours to get a result, minimum. Now, you could actually get shorter results, but it's not as accurate and so forth. You'll get more false negatives. But the point is, it takes time. And even the so-called rapid test, the antibody test and the antigen test, you have to draw some blood, take blood, you have to put it in some sort of vial or strip or whatever, and actually see some process. That takes minutes, right? Minimum. We're not talking like a PCR 4 hours. But imagine if you're going to your office and they say, we're going to take your temperature. In order to take your temperature, you have to wait 4 hours for us to take your temperature. Right? That's not going to work.
Yeah.
Okay. Instead, in fact, most people are not even patient enough to put a thermometer in their mouth and wait for 1 minute. Right? Now we do it with this infrared device, which detects temperature electromagnetically. So imagine if we can just detect say they open your mouth, or it could be COVID on your face, might be some false negatives, but they open the mouth, whatever. And we detect the presence of a specific protein in real time, just like the infrared scanner. We're not talking about minutes. We're not talking about hours. We're talking about 4 or 5 seconds, right? That's a big change. That's a big improvement. Now, the basis of this, if the frequencies are slightly different for different spike proteins and so forth, we could potentially pick up mutants too. It just depends on how the system is calibrated and its specificity and so forth. Again, in real time. And that's why I think this is very powerful, these electromagnetic approaches, because all these other approaches, as I said, depend on what we call a matter-on-matter paradigm. The reagent has to physically interact with the target.
I think we will address the last question of today. I think, okay, if we manage to utilize terahertz medicine effectively, the term surgical precision, can it be changed to like terahertz precision? And maybe can it be like less invasive than the previous surgical method?
Yeah, so let me talk a little bit more broadly about surgery and medicine. First of all, I like the way you framed that, the anonymous attendee. Terahertz precision is nice. But let me tell you a little bit of a surprise. Terahertz medicine will still be surgical. Now you're saying, oh, this guy's crazy. What's he talking about?
But can it be less invasive?
Well, yes, I didn't say more invasive. I said surgical. So in medicine with a capital M, we have two types of medicine. We have medicine with a little m, and we have surgery. For example, I graduated from the Columbia University. I got my MD from the Columbia University College of Physicians and Surgeons. And technically speaking, physicians are doctors. They're both doctors in our current world. But traditionally, historically, they were separate. You might remember the surgeons who used to be barbers. So the physicians were the medicine doctors with a small m. And the surgeons, who used to be barbers, were the surgical doctors, with the whole thing being medicine. So my point is that there are two major tracks to medicine with a capital M. There's the medicine, pharma, and there's the surgical medicine, devices. And in fact, this historical divide, this educational divide, which is still true. I mean, there are doctors who basically go into a medical specialty or those who go into surgical specialties, is also replicated in regulation. The FDA and equivalent regulatory bodies around the world has one track for drugs and the other track for devices. It's also replicated in industry. You have pharmaceutical companies and you have device companies. In fact, we call it biopharma and medtech, totally different areas. Some companies like J&J, Johnson & Johnson, the big multinational, have both a pharmaceutical and a device, but that's a real exception. In fact, J&J itself doesn't really do both. It has separate companies underneath it. Its device division, its surgical division is called Ethicon. Its pharmaceutical division is called Janssen Pharmaceuticals. It brings them together, but they're really separate. So medicine and surgery are very separate, historically, regulatory, industrially, educationally, separate. But terahertz medicine is a combination of both. In other words, it's using a device. It's like a, surgery in a local area. Remember I mentioned using the insulin receptor stimulated device over the liver. That's a surgical approach. Now, of course, you're not cutting, so it's non-invasive surgical, but it's surgical in the sense of localized disease or localized process. But it's affecting not tissues. It's not opening up and moving around and whatever. It's affecting the proteins like it was a drug. So what's interesting about terahertz precision or terahertz medicine is it's neither medicine purely nor is it surgery purely. It is truly a convergence of both, and that raises recent interesting issues. How is this going to be regulated? Is it going to fall under the pharma realm or is it going to fall under the medtech realm? Those are still open questions. And that's one reason why I wrote a novel about this, because it's not just a technical issue. It's going to be, regulatory issues, social issues, adoption, the process of medicine. It's not a complete radical fantasy, but at the same rate, it does change some paradigms significantly. And this is one of them. Sorry to interrupt, Dr. Wang. You were going to mention, but
I saw we still have one more question in the queue.
But you agree, it's a kind of surgery, right? It's not a cutting surgery, but it's a localized approach.
It's like a formless plate, which you just target on your.
That's right.
So or whatever disease.
So conceptually, it is a kind of surgery, although it's completely non-invasive.
Okay, maybe we shall take the last question from Shas Shidek. He is asking about your scanning of C19 through the saliva. The result is within 20 seconds. Is it reliable?
Yeah, I mean, I vaguely heard about that, but I can't judge. So I don't know what the basis of it is. And I guess maybe theoretically possible, but I should emphasize that the optical regime is not going to pick up specific proteins. It might look at some structural features. I mean, it's not going to pick up viruses, for example. They're just too small. So I'm not exactly sure how it works. There might be some, how should I say, residual manifestations of the virus being there. But this is really important point, is terahertz is interacting directly with the proteins. And I said in the very beginning, you know, X-rays, MRI, etc., and lack of specificity, which I mentioned later. If you do an X-ray on somebody, you can find disease, right? But actually, the X-ray itself is not probing biologically the disease process. It's looking at some sort of effect of the disease. Whereas terahertz interacting with proteins, which will be different directly in a biological way, according to a disease, will be imaging, if you will, spectroscopically, the disease. So if you have an optical scan of saliva, yeah, sure, you can pick something up. So for example, if a doctor looks at the patient and they see they're yellow because of jaundice, you know, they're not looking at individual bilirubin molecules and so forth, but they kind of get a sense that there's some effect. They look yellow, so they're sick, right? They have liver disease or hemolytic anemia or whatever. So, but it's indirect. So your saliva test is also, by definition, going to be indirect. And there's nothing wrong with that. Seeing someone completely yellow is a pretty effective way to tell that they have a problem, right? Without knowing the details. And the same with X-rays. X-rays pick up a lot of things, but they are fundamentally indirect. Whereas one of the power of this approach is that it's not indirect. You are probing the actual biology. For example, if you have a cancer, if you have cancer proteins, you say you have cancer proteins. You don't, right? Not some derivative effect, which I'm not saying is wrong, but it's derivative. And to answer the question about optical scanning of COVID-19, or more precisely SARS coronavirus 2, it has to be an indirect method.
I think this means that it gives a definite answer to whether you have that.
Potentially, this is going to be more direct, more definitive.
Thank you. I think we come to the end of the presentation. We would like to say thanks again to Dr. Ogan Gurel and also our audience for your time and participation in this webinar. Hopefully this will be beneficial for everybody, and thank you for your attention.
Thank you for moderating, Dr. Wong. Thanks to our organizers, and of course, thanks to the audience as well for the great questions and engagement. My pleasure.
Okay, see you.
All right, thank you.